This is a video about ionic bonding. This is part 2, dealing with the Electron Dot Model for representative elements only for ionic bonding. Ionic bonding is when one atom loses valence electrons to become a positive ion and another atom gains those same valence electrons to become a negative ion. That's electron transfer. The oppositely charged ions that are created then attract each other, and that's known as an ionic bond. All electrons are accounted for in this process according to the law of conservation of mass, which says that you can't make things disappear into nowhere or appear out of nowhere. So the number of electrons lost in creating the positive ion equals the number of electrons gained in creating the negative ion. This is also in keeping with the law of electrostatics, which says that opposite charges attract and like charges repel. Before we get going, a quick review. The quantum mechanics model of the atom is going to be used here. The quantum mechanics model can be expressed with the diagonal rule. It's important to realize that only S and P sublevel electrons get involved in bonding. We know by experimentation that D and F sublevel electrons only play an indirect role in bonding. So we're going to pay attention to the S and P sublevel electrons, specifically on the outside of the atom. The word valence in Latin means outside. So valence electrons are the outside or outermost S and P sublevel electrons on an atom. And we have a rule that we call the Octet Rule. An octet is a group of 8. 8 valence electrons is the most stable arrangement. Atoms will gain or lose electrons, valence electrons, to form ions with 8 valence electrons. In other words, so that they end with S2P6. Now, we can take a look across the periodic table and see that electron configurations for different elements that are in the representative element part of the periodic table can be determined. Their elements in this column will end up making a 1+ charge, and they will have an electron configuration as an ion that looks like sodium, for example. Here we have 11 protons in the sodium nucleus. Na is sodium. Notice it has 1s2, 2s2, 2p6, 3s1. That totals out to be 11 electrons. 2 more is 4, 6 more is 10, 1 more is 11. It's neutral here. 11 protons, 11 electrons. If we give one of those electrons away, specifically the 3s1 electron, which is the valence electron on neutral sodium, it becomes Na1+. 11 protons and 10 electrons. And notice that there's a new octet. Now energy level 2s and 2p becomes the new outside of the atom. And that's why sodium and every element within that column forms a 1+ charge. Jump to the opposite side of the table and we can take a look at chlorine. Chlorine, when it's neutral, and you can see here it's in the 1- column, has 17 protons and 1s2, 2s2, 2p6, 3s2, 3p5, 17 electrons. It's neutral, but when we give it one more electron, we can see that it'll have an octet. So 3p5 becomes 3p6, and now 3s2 and 3p6 makes an octet. It makes 8 valence electrons. Notice we have 17 protons and 18 electrons. That's one extra electron, and that's a 1- charge. So we can represent bonding using electron configurations. For example, here we have NaCl, where we have Na1+ and Cl1-. And what happens is this one electron from the sodium atom is given away and taken in by chlorine, which goes from 3p5 to 3p6. So we end up with a positive ion that has an octet and a negative ion that has an octet. And these two ions attract each other because opposites attract according to the law of electrostatics. The problem is this is not an easy way to model bonding. So we need to find something better. So what we do is use what's called an electron dot model for atoms. So here's an example of an electron dot model for a sodium atom. So you can see that we have 11 protons in the nucleus, and with the quantum mechanics model, 1s2, 2s2, 2p6, 3s1, this is an electron configuration. We see 11 electrons outside the nucleus. The outermost S and P electrons are the valence electrons, and all those other electrons on the inside can be considered to be core electrons. So what we do is we represent this atom with a different model. This is called an electron dot model. Na, the letter symbol for sodium, represents the nucleus and all the core electrons. So the 11 protons, any neutrons that are also in the nucleus, and these electrons are represented by the symbol Na. And then this one valence electron is represented by the dot. So that's an example with sodium. Here's an example with chlorine. Here's the quantum mechanics model of chlorine. 17 protons in the nucleus, core electrons, 7 valence electrons for 17 electrons total. The letter symbol Cl represents the nucleus and all the core electrons for chlorine. And then there are 7 dots representative of these 7 valence electrons, S2P5, right? 2 and 5 make 7. We have 7 dots there. Those are the valence electrons. So this allows us to really just focus on the valence electrons of the atoms. All right, so then moving forward, let's take a look at how we can make electron dot structures for ions. So here's an example with sodium and chlorine again. And what we see is a sodium atom, and it has 1 dot representative of that 1 valence electron in the 3s1 position. And here's an example of a sodium ion. Now we've taken that 1 dot away. Sodium ion with a 1 plus charge now has an octet with 2s2 and 2p6 filled up. Notice 11 protons, 10 electrons for the 1 plus charge. And notice that we no longer represent the dot because we've taken that dot away when we take away that 3s1 electron. Now contrast that with chlorine when it forms an ion. Here's the quantum mechanics model for chlorine. Here's the electron dot model for chlorine. When chlorine forms an octet, it gains an electron and goes from 3s2,3p5 to 3s2,3p6. Now it has a total of 17 protons and 18 electrons. That's 1 extra electron. It gives it a 1 minus charge. But it also gained a dot because it took on 1 more electron in that 3p position, going from 3p5 to 3p6. So now it has 8 dots, and that's representative of the octet, 8 valence electrons. So we can use electron dots to represent ionic bonding. And here's an example of the 2 steps for making a sodium chloride compound. And there are 2 steps in the electron dot model for ionic bonding. What we do is we write the electron dot structures for the atom in question. And if you look at the formula, NaCl, that's 1 sodium, Na, and 1 Cl. Now in formulas, we typically don't write the 1s in there, but you could write a 1 right here and a 1 right there if you wanted to. So 1 sodium, 1 chlorine electron dot models. The first step is to write the electron dot structures for the atoms and then use an arrow to show the movement of electrons. And what's going to happen is this electron is going to leave sodium and go on to chlorine. The next step is to write the ions that result. We get Na 1 plus ion and Cl 1 minus ion. Notice that the positive ions always have no dots. They get rid of all their electrons. We can see that looking back up here, for example, sodium gave away its 1 dot to get an octet. And that's what we see, no dots here because it gave away that 1 dot it had. And then negative ions will always have 8 dots. They will always be that way. Positive ions with no dots, negative ions with 8 dots. So we write the electron dot structures for the ions that result when we move those dots. And be sure to include the charges when you write those ions because, of course, ions are charged atoms. Now remember that we have octets on both of these species. The Na1 plus has an octet and the Cl1 minus has an octet. So ionic bonding is very stable because the elements involved all have octets. Let's take a look at how the electron dot model is put together and how it relates to the quantum mechanical model. Let's do this for chlorine. Chlorine, when it's neutral, is 1s2, 2s2, 2p6, 3s2, 3p5. These are the valence electrons out here. And what we're going to do is focus on those valence electrons. Let's draw an orbital diagram for these electrons. the valence electrons here. We have 3s with 2 electrons, so up arrow, down arrow, that's 2 electrons. And then 3p fills up with 5 electrons. Remember the order here? Up, 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 down, down. So that's 1, 2, 3, 4, 5 electrons in the p position, 2 electrons in the s position, for a total of 7 valence electrons. Notice we have 4 orbitals that could fill up with valence electrons there. That's always true for valence electrons. There's always 4 orbitals available, 1 s orbital and 3 p orbitals. So we can treat these orbitals, these s and p orbitals in question, as if they have equal energy. So that means if we're increasing energy as we move up the diagram, we're going to write these as if they have the same horizontal level. Now when we fill in electrons, we would do it this way. Up, 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 down, down, down. So that's 7 valence electrons, filling them up as if they all had the same energy, equal energy. So what we do for an electron dot structure is we just write the symbol, the letter symbol for the element, and this represents the nucleus and all the inner electrons, and then we could put those orbitals around an imaginary box around that symbol. So I've filled the box in here so you can see it. You can see how I have the orbitals distributed there, and we would put the electrons in. According to the law of electrostatics, they'd be as far apart as possible, right? Electrons repel each other. So up, 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 and then down, 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 and we have 7 electrons represented here. So rather than using arrows to represent those electrons, we can use dots. So let's put the dots in. 1, 2, 3, 4, 1 in each orbital available. And then continuing on, pairing up because now we have to, 5, 6, and keep the pairs apart if you can. 7 makes our 7 valence electrons. So we just omit the blank lines for the orbitals, and we use dots instead of arrows to represent the electrons, and this is an electron dot structure. And that's how it relates to what we had been using previously for models of the atom. Now remember, you can use whatever models you have. We try to model nature to take advantage of what makes it simpler for us. And sometimes models have things that work well and things that are not exactly perfect, and we just kind of live with that. So understanding the limitations of every model that we use. We can determine the valence electrons for representative elements, remembering that all elements in the same group have the same number of valence electrons. So if we go across period 3, and I have that highlighted here, the number of valence electrons in each group would be 1, 2, 3, 4, 5, 6, 7, 8. And we can see that if we look at the electron configurations a little bit more closely. Oops. We can see we have, again going across the period 3 elements, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Sodium ends with 3s1. Magnesium's electron configuration ends with 3s2, so sodium has 1 valence electron, magnesium has 2. Aluminum ends with 3s2, 3p1, it has 3. 3s2, 3p2 is 4. 3s2, 3p3 is 5. 3s2, 3p4 is 6. 3s2, 3p5 is 7. And finally 3s2, 3p6 is 8. That's where we get 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And again, all the elements within that group, and I just cut the bottom part of the periodic table off there, all the elements within those groups of the representative elements would have that number of valence electrons. So now let's go across the period 3 again and write the electron dot model for representative elements using period 3 as our example. Again, we're using the law of electrostatics that opposite charges attract and like charges repel. More specifically, like charges repel, because electrons are all negative. They will repel each other and be as far apart as possible. Now this is a two-dimensional model, but it actually is a pretty good predictor, especially when we get to covalent compounds, for the two-dimensional and then later on the three-dimensional structure of molecules. It's a little bit limiting to use electron dot models for ionic bonding, but since we do use them for our other type of bonding, covalent bonding, we are going to consider them here. So as we go across the periodic table, we see 1, 2, 3, 4, 5, 6, 7, 8 going across the representative elements. Elements in period 3, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. You can actually make a few different valid electron dot structures. You could put the 1 dot for the 1 valence electron there, or you could put it here, or you could put it here, or you could put it here. Any one of those would be valid electron dot structures for sodium. For magnesium, we have 2 electrons, 2 valence electrons. So we're going to put those dots as far apart as possible, either left, right, or top, bottom. For aluminum, let's go left, right, top. Let's go top, bottom, right, and then left, right, bottom. And then we could go bottom, right, bottom, top, right in that order, I guess. And then finally, it looks like we could go, actually, I'm sorry, we put that in the wrong spot. Our aluminum is from that period, so we could go there, there, and there. And we would have electrons as far apart as possible for those positions for those electrons. For silicon, there are 4 valence electrons. So what we can do is just put them left, right, bottom, top. We're trying to keep the electrons as far apart as possible in those imaginary orbitals around an imaginary box representing this symbol. This is our model called the Electron Dot Model. There are 5 valence electrons for phosphorus, so we could put them in like this, or like this, or like this, or like this. And notice that any one of those would have the pair of electrons on any side and the single electrons apart from each other. Again, we're trying to keep the valence electrons as far apart as possible because like charges repel. It seems like it would be almost unrealistically simplistic for this to be a useful model, but it turns out it's actually very useful, especially when we're trying to deal with covalent bonding and the production of molecules. All right, for sulfur, there are 6 valence electrons, so we're going to put them in left, right, top, bottom, and then we're going to go top and bottom again, and we could go left, right, top, bottom, and left and right. Again, I'm just trying to keep electrons as far apart as possible, so I don't want to put the pairs of electrons next to each other. If I did something like this and had the electrons next to each other like that, that would not be a correct structure. That's not a valid electron dot structure. With 7 valence electrons, we can put them in so that the single dot is on the right. We can put them in so that the single dot is on the left. We could put them in so the single dot is on top. And we could put the electron dots in so the single dot is on the bottom. And with argon, there are 8 valence electrons. The positions are completely full. Now, these are all possible structures you can put together. There's really no exact pattern you have to follow, but we want to keep electrons as far apart as possible. So notice that when we have 3 electrons, we're not going to pair any up. When we have 4 electrons, we don't pair any up. When we have 5 electrons, there should be a single pair, and it could go on the top, on the right, on the bottom, or on the left. With 6 electrons, there's going to end up being 2 pairs, and they could go top, bottom, or the 2 pairs could go left, right. If you have 3 pairs of electrons, we're just not going to put them next to each other. I guess there's really no wrong way to do that because you're going to have 1 electron singled out. So you can see how that works for those different possibilities. All right, the electron dot method for ionic bonding has, again, 2 steps. Write the electron dot models for the atoms in question and use arrows to show electron movement, and then write electron dot models for the ions that get formed once you move those electrons. Remember, positive ions always have no dots, and negative ions always have 8 dots. Let's do a couple examples here. For magnesium chloride, there's 1 magnesium and 2 chlorides. Now, there's not a 1 written in that formula, but we can just infer that if there's not a number there, that must be 1. That means we have 1 magnesium and we have 2 chlorines. Now, we can look at a periodic table at the location of these elements to determine the charge that they have. So magnesium, we're going to look at the number of valence electrons here first. Magnesium is in this group on the periodic table. It's going to have 2 valence electrons, so we're going to put those electrons top, bottom. Chlorine is over in this column. It has 7 valence electrons, so we're going to go top, bottom, left, right, top, bottom, left, and let's do that again. Now let's use an arrow to show how the electrons would move. We're going to take this electron and move it over by that opening on chlorine to make a pair, and take this electron and move it over here on that chlorine to make a pair. So we end up with one magnesium ion with a 2+ charge, and we end up with 2 chloride ions. Each is going to have a 1- charge. Because each chlorine gained a single negative electron, that gives it a 1-, gaining a single electron. And each magnesium, or that one magnesium there, lost 2 electrons. So losing 2 negatives means there's an overall 2+ charge. It doesn't have the 2 negatives that it needs to be neutral. Again, notice that the positive ion has no dots and the negative ion has 8 dots. So we had to peel away 2 electrons to get to the octet underneath. And then we have an octet here by adding electrons on. So we still have octets on all these. We're going to take a look at what this forms in a later video in terms of a macroscopic view. In a large scale, what does magnesium chloride form? But on a particle scale, we can see that the smallest piece of a compound you could call magnesium chloride would have 1 of these ions and 2 of these ions. So when you look at a formula like that, and you know how bonding works, and now you do because you're learning this now, you know that that's made of 1 magnesium ion and 2 chloride ions. And you could look at a periodic table to determine the structure of those ions, the charges, and so on. Let's do this with a little bit more of a complicated example. Here's aluminum oxide. It's made with 2 aluminums and 3 oxygens. So let's go ahead and put 2 aluminum atoms in there. And if we look at where aluminum is located on the periodic table, it's right here. So it has 3 valence electrons. Let's put 3 dots in. We'll go top, bottom, left, and top, bottom, left. And 3 oxygens. So 1, 2, 3. Oxygens are in the group that has 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Remember that when you put the dots in, we want to keep them as far apart as possible. Let's show how the dots move, and our only rule here is pair up the electrons where we can and get rid of all the electrons on the aluminums. So we can fill up those 2 open positions in oxygen with these 2 electrons. Do what you can to try to not cross the arrows so that it doesn't end up looking like a big bowl of spaghetti there. And we end up with the electrons moving away from the aluminums and filling in those open positions on the oxygens. Notice that each aluminum lost 1, 2, 3 electrons, so that gives them each a 3+ charge, right? 1, 2, 3 electrons there as well. Notice that each oxygen gained 1, 2 electrons, so each oxygen is going to have a 2- charge. Now for the aluminum, getting rid of the electrons means they have no dots. Now that they do have an octet, but the electrons that were the dots before are now gone. And the oxygens are gaining electrons so that they have 8 valence electrons. And there we go, the 8 dots. So if you understand what we did in this video, then you should be able to write electron dots for elements from the representative part of the table. And I'm going to ask you to do that for these 5 compounds. Write the Electron Dot the Electron Dot Model, and make sure you show 2 steps for that for the 5 compounds below. Remember, the first step is to write the electron dot structures for the atoms and show how electrons move with arrows. The second step is to write the electron dots for all of the ions that get produced and put the dots and the charges in there. So, sodium fluoride, calcium sulfide, 1 sodium, 1 fluoride, 1 calcium, 1 sulfide. Sodium oxide, this is made of 2 sodium, Na is sodium, and 1 oxide. Aluminum nitride, 1 aluminum, 1 nitride, and aluminum sulfide, which is made of 1 aluminum atom and 3 sulfides. Good luck.